So when we're talking about cavity barriers and fire stops, we're looking at obviously protecting these facades against the spread of fire and also smoke. Within this presentation, what I'm going to go through is mainly from a manufacturer's perspective or our perspective, what we need to do to achieve manufacturing products that will successfully help protect our buildings that we live and work in. So first of all, I'll go through what a cavity barrier or fire stop are. A lot of you put your hands up, which is always a good sign, but some of the specific details that they need to function, some things that you might not know about or even think about. Then got some of the regulations, which obviously the previous slides of that we've seen this morning or this afternoon have really gone into some details as to how we're starting to change within Denmark and what we need to do better. Obviously in England or the United Kingdom, there's been a lot of changes post the tragedy at Grenfell, and we're learning a lot, and I think it's fair to say worldwide we're all starting to make changes and learn more. So it's mainly looking at some of the perhaps best practice or highlighting on this compartmentation. We're then going to look at some testing, which again we've looked into some standards, but these were specific to cavity barriers, just to give an idea of how they're tested. And then we're looking at a couple of specific applications for fire stops and cavity barriers. So we're looking at curtain wall structure and cladding or ventilated facades. So let's jump in. What is a fire stop or a cavity barrier? Well, in the United Kingdom, we've got, we're actually split into the 4 different countries, England, Wales, and Scotland and Northern Ireland, and each have slightly different documents which give us guidance, but they all say the same thing, which is a definition of a cavity barrier and fire stop. And it's very specific as to the 2 different terms. They're not actually the same thing. They fit into many different facade types. Obviously, we have all different kinds of facades on building, going from your curtain wall, your masonry, and then you have different forms of cladding or lightweight sealed systems. And it's actually quite different which goes into which, as the applications are dictating quite different kinds of criteria. So in terms of the definitions, and that's, again, apologies, a lot of English small text up on there. So I'll go through basically what they are. But starting off with a cavity barrier is defined as a product that's installed into a concealed space, into a cavity. So usually these are areas that are hidden away, they're not easily accessible, and firefighters may not be able to actually get to them, or it may not be possible to install things like sprinkler systems and other protection into that cavity. So they're specifically in a concealed space or a hidden space. And the idea is that they're to slow that spread of fire and smoke through that space. You then have a slightly different variation of a cavity barrier, which is actually formed from the invention of barriers specifically for rain screen or cladding, and that's an open state cavity barrier. An open state cavity barrier is the same as a cavity barrier, intended to install into a concealed space. However, it's actually reactive. It's inherently there to allow for ventilation and drainage of the system. So a open state cavity barrier, the idea is that it's installed into a cavity where you might need drainage or ventilation, so air movement. So you can't just block it off. You need to allow for that air movement and that drainage. So an open state cavity barrier remains open, allows for this gap, but then in the event of a fire, it reacts, kicks in, and it closes off that gap and stops that fire and smoke spreading. You then have fire stops, which typically are a heavy-duty product here. Cavity barriers usually have lower performance requirements. However, the fire stop is seen as a continuation of compartment zones. So we'll go into a bit more about compartment zones and where exactly these 3 different products actually fit in. So when generally talking about testing fire stops and cavity barriers, we're looking at a couple of different criteria, and hopefully some of you have heard or are familiar with these 2 different terms, which is integrity and insulation. So there's many ways that when you test products for fire, things that you have load bearing, capacity, structural, that sort of thing. But with cavity barriers and fire stops, because they're not a structural component, it's just these two different criteria, this integrity and insulation. And integrity basically means that you're trying to prevent physically that fire from moving from one space to another. So physically blocking it, something like a sheet of steel would be brilliant because that's got a high melting temperature and it will stop that fire from physically moving from one room to another. However, the second criteria there, the insulation, the steel wouldn't be so good at. And that's based on the idea that you can have spontaneous combustion happening on a non-fire side of a product via the heat transfer. And most standards that you'll find, European and British, are set based on a difference of 180 degrees Celsius from the non-fire side to the fire side. So as soon as you're measuring above 180 degrees plus the ambient temperature, then it would actually be failing that insulation part of the test. Now, when you think most furnaces are set to about 1,000 to 1,200 degrees Celsius, it's got to absorb a lot of temperature. That's a lot of heat that it's got to dissipate to successfully give you an insulation rating. And that's always the harder part of the test. So, as I say, when we're looking at fire stops, cavity barriers, either or product, any of the three we've just looked at, we're testing for that integrity and insulation. And that obviously poses some difficulties, especially with the open state one. Now, as we've gone to, and I won't go into too much detail because you're far more familiar, and previous presentations have brilliantly explained some of the changes, and also this afternoon some more about local regulations and how we should be aiming and striving for better. But generally, there's a real emphasis, and it's great to hear, on compartmentation. It's this subdividing buildings and ensuring that fire and smoke is slowed as much as possible as it can from spreading around. So it's something that, as a company, Siderise, we're all about. Our products are all about maintaining compartmentation. Obviously, it's great to hear that that's very much the site that we're going down locally. So I keep saying compartmentation. In really basic terms, the way that we look at it, at the very least within the UK, is we utilise certain components of that building as the compartment lines. You have your floor slabs, you're separating floors. That's obviously a different compartment from floor to floor. And then any wall which is dividing any sort of dwelling, so an occupied space, and fire escapes, things like that. Those are all compartment lines. Now, when we're talking about fire stops generally are inside the building, and they'll be found in places where you've got gaps between different compartment lines. So say you've got a curtain wall facade and you've got a floor slab, you'll have a movement gap to allow for the deflection of that lightweight facade. That gap would let fire and smoke spread through it. So what you need to do is put a fire stop in there. And the reason it's a fire stop is it's seen as it's a continuation of that compartment line. So it needs to meet the integrity and insulation of that floor slab or of that wall. A cavity barrier is actually set differently, where it's got a specific, and again it depends where in the UK even what the requirement is, but it will have a specific set performance requirement, typically around 30 minutes. In England and Wales, it's 30 minutes integrity and only 15 minutes insulation. In Scotland, it's only 30 minutes. There's no insulation rating. Now, the reason for that is we've got to bear in mind this is a concealed space or a hidden space. It's a cavity where you're not going to be able to put additional protection. So you're going to be limited as to how much you can protect that space as it is. But also, generally, these concealed spaces, the other elements around it, such as the lightweight facade, say on ventilated systems, will not be able to actually put up with a fire potentially for as long as other components like reinforced concrete against reinforced concrete. So generally the requirements are lower on those cavity barriers. Not to say that we don't find buildings often upgrading beyond what regulations ask for, which again I think is an important message here, is what's regulatory isn't necessarily what we should be doing. Sometimes it should actually be better than that. We should all be striving for best practice. So quite often you'll find cavity barriers are actually increased in performance on specifications, but they'll have a minimum set by the regulation. So when we're, again, just wrapping up on a bit of testing here, there's, again, a couple of different types of testing that generally we're looking at with cavity barriers and fire stops and many products. One is your reaction to fire, which is obviously giving your Euroclass rating, so non-combustible, your A1s, A2s, Bs, and then obviously with your smoke emissions and burning droplets, you have S and D values. The reaction to fire is based on obviously set standards to give you that classification, and it will tell you how, in theory, that product will react or behave in that fire. But then the important bit with the integrity and the insulation that we're testing for with cavity barriers and fire stops is that of fire resistance as opposed to reaction to fire. And fire resistance is measured in time, simply. It's in minutes, and it's generally measured in 30-minute intervals. So you'll find it's a 30-minute or a 60, 2-hour, things like that. So the important thing is, when we're ever looking at cavity barriers, we should always be looking out for that fire resistance. Usually, a fire stop or cavity barrier will be a Class A1 naturally to give that fire resistance. But that's not always the case, as we'll see on a couple of barriers going forward. So these are some of the specific tests that we're looking at. Now in the UK, despite Brexit and everything like that, we've made the wise decision to continue using European standards because we need a collaborative approach to making buildings safer. And obviously, from a financial perspective, as a company manufacturer, we want to still sell to our European partners. So we're looking at these European standards, which in the UK, as I say, also supersede British standards where they're available. And one of the first ones that we look at, which supersedes or has replaced a bit of an overused old British standard, is the EN 1366 Part 4. And you'll see this standard pop up a lot. It's quite a wide capturing test. It allows for testing a lot of different kinds of applications. It's based on a product being installed just within an aperture of concrete. So you have just an aerated concrete frame and then the product installed. That's mounted to the furnace, and then you measure how long it takes for that temperature to get through it, and then how long it takes the fire to actually break through it physically. And that gives you your fire stop or cavity barrier rating by 1366 Part 4. So it's a great test in terms of showing what kind of longevity a product will have, but in a very static environment. Everything's still, it's moving, it's not moving. You can, at the very beginning of the test, actually apply one movement, so you could sort of compress the material or expand it or move in a shear direction, but that's before the test starts, and it's not then recycled throughout the test or continued after that. So you should always look at the 1366 Part 4 is very much applicable to things like services where you've got pipes going through walls. It's not expected there's going to be much movement, not necessarily against the back of a facade system. That's not to say not always the case. With curtain wall systems, very specifically, we have the 1364 Part 4, very similar number. But this product, or this test, is specifically to test horizontal fire stops to the back of a curtain wall system. And it's a fantastic test. It's very important because in this test, it's more of a system test than just between concrete lintels. You actually have a curtain wall facade system that is installed in place, a floor slab that's not just concrete lintels, but an actual floor slab specified for the project or for what you're wanting to test. And then you install your fire stop into that system. So in reality, when you're testing this, what happens is rather than concrete just being fairly robust as it typically would be, combined with the size of the test, things start to move. And when you're looking for generally around 2 hours or more, it means it's got a lot of time for all these different components to heat up and starting to flex. So that curtain wall will start to buckle. There's no sprinklers to cool it down. Obviously, it's a furnace. So it will start to buckle. that movement gap where the fire stop's installed will start expanding and compressing. And it'll start contorting and moving in different weird and wonderful ways. So what ends up happening is that fire stop is stretched to its limitations throughout that test. And then in addition to that, another part which makes this a lot more realistic, a lot more true to life, is, well, we're giving a design life of 60 plus years. What's to say if this product's been in that building for 60 years' time and it's been moving because of the deflection, wind loads and things like that, it's been compressed and it's been weathered or aged, who's to say it will still work in 60 years after all that movement? So you can add, and I'll show another slide in a little bit, you actually add a cyclic moving part of this test at the beginning, where it will cycle that compression and expansion over 500 times before it goes into the test. So you've essentially artificially weathered and aged that product before it actually gets tested. So again, bringing true life and more of this system holistic approach to the actual testing. Jumping back to cavity barriers quickly, this one is this unique open state cavity barrier. Originally, because it's so different, you couldn't really test it to a standard like 1366 Part 4 because you've got this ventilation gap, it's open. And because of health and safety, you couldn't turn the furnace on when there's a gap in the furnace. So it would basically be tested by assessment or be assessed rather than tested. And it took a good few years of becoming more and more popular to use within certain facade types, like this cladding or rain screen, for there to be an actual sort of outcry for we need a standard to test it against. So the ASFP, which is very similar to the BBN within locally, it's basically set up this test standard based on 1366 Part 4 called the Technical Guidance Document 19. It is being adopted into European standards, slightly different, and it has been going on for a long time, so that may even be slightly up to date, the pre-EN number there. It may well or may be included into its own element, or it may be remaining in that one. Time will tell. But essentially, it's a way of testing these open state barriers. It just has a couple of caveats saying, we'll start the furnace, but we're not going to fail it for integrity because you've got a gap there and it needs time to react. So we're not going to fail it for that first 5 minutes, which arguably I think is a long time, 5 minutes still. We were pushing them for 2.5 minutes, but 5 minutes it is. So once it hits that 5-minute timer, then if that gap hasn't closed, if that cavity barrier hasn't successfully sealed and regained integrity, then you'll fail the test instantly. So there's these little caveats like that. It's installed in an upstand, as you can see. It's actually, rather than just a flat furnace, you've got an upstand to include thermal insulations. Now, the idea originally in TGD 19 is then you would install your different thermal insulations above and beyond, below that cavity barrier, and then that would be proof that that thermal insulation could be used with that cavity barrier. And you had essentially a ranking of the combustibility or potential combustibility of different products, which would then allow you to test with a specific insulation and then use anything that was ranked below that. So this open state testing is, as I say, become very much going forward the way that we're testing these open state barriers, and hopefully you've started to see them quite commonly going into these rain screen facades, as it's the only real way to protect them but maintain this drainage and ventilation. That's where I was starting to get to with that curtain wall test, but quickly wanted to go through that open state one, is the importance of system testing. Again, I think another very important point here, and we, as a manufacturer of just a single component, just these products that are fire stops or cavity barriers, they're only one piece of the puzzle, one piece of that system that goes together. And it's vital that all of the pieces that go together within the system work together as best possible to prevent that fire and smoke spread as best possible. So we have, and we've already gone through in the previous presentation some fantastic, and then again, apologies trying to keep up with only speaking English. The diagrams were very helpful in seeing where we were looking at in terms of the standards. But we're looking at these massive system scale tests where we're putting the cladding with all the different components as intended to be built on that project. And we run a test and we can see how it reacts, how these different components work. And most importantly, it's true to life, or trying to be as true to life scenario, because it's only when we get to these different, or this closeness to being as built, that we start learning some of the very fine details that actually make a very big difference. An example of that is we as a company have, obviously, as I say, only been the cavity barriers, but we've been involved with many different manufacturers and partners on the 8414 tests, British Standard, and NFPA 285s, which are the American slightly different equivalent, and also some of the Australian and other standards that are very similar to this. We've conducted or been partnered in over 250 of these large-scale tests. So it's been a long journey, but we've learned quite a lot, and especially with some of our partners that frequently we've tested with, we've been able to test some very minute differences or learn some minute differences. So things like the joint or the gap size between panels, you don't realise actually how significant of an impact that has on fire spread, just by the virtue of it allowing more air and oxygen into that cavity to get sucked into the cavity. So it makes a difference. You think it's only a difference between 10 and 5 mil or 4 mil. It doesn't look much different, but it reacts differently. Things like the cavity barrier location. Quite often it's not even really thought about. You think, okay, the cavity barrier needs to be at the edge of the floor slab, but where is it in regards to the actual joint on the panels? You put the joint of the panel above the cavity barrier, and then as that panel below starts to burn away and the fire's breaking out, then the actual vortexing effect and sort of you get a vacuum happening through that gap in the panels above, and it just sucks the fire back up around, bypassing that cavity barrier. Whereas if it's below it, then it will last for as long as that cavity barrier is, and as long as that fire's just attacking the outside of the facade. So all these minute or what seem like very small differences can have a huge impact. And again, as I say, and I make a real point of it, is system tests, working together, working as close to as built as possible, is vital to learn this kind of information. Another big important part of testing is, whilst we'll use a third-party test facility to run these tests, it's also important to then have them assessed and certified by third-party bodies. And this essentially gives a far more confidence and an easier way to specify products, knowing that it's not just a manufacturer has gone and tested a product, but it's also been assessed and you're being given a slight field of applications, so it's as close to as built as possible. And you have many different certification bodies for all different kinds of tests, which is something that, again, we really believe in. Because another part of certification is not just checking that it's been tested right, but also it gives you essentially an expiry date. With test data, it doesn't really have an expiry date. It's just results. It's pages of data and information. But we manufacture products. As a factory, we're constantly trying to, or striving to be more eco-friendly, environmentally friendly. Our supply chains may break down. The product changes over time. So it might be different materials. It might be put together slightly differently to be more efficient. Who's to say that product 5 years later will test and react the same as it did in that test? So that's where certification comes in, and we're constantly audited. You get surprise visits from the certification body that come and check everything's the same. Any differences at all, then you might be forced to retest. Or if it's an insignificant change, they may say, as long as the data is similar for the core products or what have you, then that's fine. But it basically is the police of test data, which is very important. So now we're just going to go a bit more specifically into the couple of applications. So curtain wall, which is a little bit more probably robust in certain ways. Many different countries have many different approaches to protecting that movement gap. But some of the important things, or one of the most important things I'd argue to consider with curtain wall applications is whilst it seems like quite a solid facade, it does flex and move. There is dynamic movement within that facade. Just from people going in, the live loading, furniture and things will start to deflect floor slabs and it will start pulling and warping that facade. And the wind brushing against it, especially as you get taller towers, are also going to be deflecting that facade in different ways. So hence we have those movement gaps to allow for that without aging prematurely, things like the glass, or putting additional stress to the glass. So with all this movement, logically, the product that we installed into a movement gap has to accommodate that movement. It has to be able to move and flex, but not deteriorate over time, as we've touched on that testing earlier. Now, the other thing with curtain wall to bear in mind is usually we're looking at using aluminium. Obviously, we do have things like steel systems available, but I think it's fair to say they're quite uncommon. Typically, it's aluminium that's being used. And as we've seen as well from previous presentations, aluminium, we're looking at these lower melting points and we're looking at these systems where there's going to be a much faster disintegration because of just the material properties. Typically with aluminium, you're losing pretty much all of its structural strength by the time you're getting to 350 degrees. By the time you're getting to about 600 degrees, it's vaporizing, it's disappearing, it's just completely gone. So with the whole wall or facade built of that and glass being as heavy as it is, as we all know, you can imagine that this facade is actually fairly delicate despite its appearances, in the event of a fire at least. So again, with these lower melting points, we need to consider that it's moving already. It only takes the early stages of a fire to actually heat up where it's going to flex and deflect even more, because that strength or that structural strength is being lost very quickly in a fire. So what might be only a 10, 15 millimeter gap that it typically will move, you might find it starts moving 20, 30 millimeters in the event of a fire. And that's where this movement of that product comes in, that Firestop product. So just putting in a bit of stone wool or non-combustible material and steel plates, which is around the world quite a common approach of actually sealing that gap, may not be suitable depending on that movement or the performance of that assembly, that system. You need a product that's actually going to be tested against that movement, but then also will actually perform in the fire when it's been moved around a lot and squashed in that cavity or that movement gap. So it's something that we've for many years been calling out, and our product, our unique product that we started in the early 90s selling, was specifically for this application. So we take typical stone wool, which is manufactured in a horizontal fibre, rotate it 90 degrees in the factory, compress it, and then actually apply foil faces to that. So there's actually compression built into the product before it gets to site. And then with a small amount extra compression into that movement gap, just to allow for your deflections or your typical deflection, that means that there's a lot of compression in that product with very little effort, that in the event of a fire, that foil facing reacts, burns off very quickly as designed, and it releases that product, that fibre, which is now running vertically. So you actually got the air inside it expanding and compressing. Whereas a horizontal fibre material, it's essentially very brittle because you've got these fibres running across. They're usually made of a volcanic rock, and they're just very, very thin strands of rock. So as soon as you start pressing them together, it will bow and then it will snap. And it only takes a small amount of time, a surprisingly small amount of time, for that sort of cyclic movement of the facade back and forth, for more and more of those fibres to break, and then it remains compressed and it can't expand back out. So it's all about the engineering of that fibre. It always looks very silly and sounds very silly as it's just a bit of stone wool, but actually it's some very clever science behind it. And this is where, as I say, we have that EAD, and forgive me, I can never remember the number for it because it's a long number. I'm not even going to read that out. You can see on screen it's quite a long one. But this EAD is what's part of that 1364 Part 4 test. And that's, as I say, over 500 cycles of movement that's applied directly to that testing assembly. You can see it's with curtain wall and all, it's the system itself. And then that is just dropped onto the top of a furnace and then burnt for however long you can achieve, essentially. So again, it's this as-built environment, trying to test as best possible, as closely as possible to what we're building, so that we know that it's going to actually keep us safe when we're working and living in these buildings. Now, another thing that comes with this test standard is actually the, as I say, the system itself. And again, this aluminium, or typically aluminium curtain wall system, it's going to disintegrate over time. So as you can imagine, actually during that test, if you've got an exposed bit of curtain wall below the fire stop, surely that's being attacked, and that's going to be a weak point or potential weak point. And you're quite right, it is. And that's where we get to the point of actually having protected spandrel zones. So these areas at the edge of the floor slab having a minimum amount of fire resistance to actually ensure that that fire can't break through and out of that facade. As otherwise you'll get this leapfrog effect, which is very hard to fight against anyway, but you reduce the chances of this leapfrog. And that's where you have, as you can see in the 4 stages there, your early stage of the fire, the ignition, is just starting in that room. You end up with flashover, where essentially the whole room's on fire. Tends to happen at about 600 degrees Celsius in that room, which is only usually 5 to 10 minutes into that fire. And then once you reach flashover, everything's burning. Everything's trying to just disintegrate. It's just a matter of time now. So you will get that breakout. Glass will shatter. The aluminium will vaporize at this point. Fire will be breaking out of that building. And it'll be trying to then, depending on wind and the sort of location and temperatures, it will start attacking the facade above it. It'll naturally be branching out. And then over, again, just a period of time, it's going to break into that upper glass. It's going to basically bypass that fire stop by breaking out and then back in. So building that spandrel panel, or that zone in front of it, as tall as possible with a fire resistance, means that fire has to break out much lower down and stretch much further up to try and actually bypass that system. So even without fire-rated glass in the actual visual areas, it means you can achieve with a large spandrel, protected spandrel panel, a good amount of protection against the leapfrog effect. So just wrapping up in terms of these different ways that we tend to look at them, is you have what's called a Type A system, and that is a non-fire-rated facade type. And quite often you'll see, even in the UK still, we're trying hard and but a lot of different associations are really pushing it. We're nearly there. Is you may find things like the 1366 Part 6 or Part 4 testing of products within a Type A facade. It shouldn't really be done. You can get away with that, however, in a Type B facade, which is a fire-rated facade. So you'd be looking at different components. It's not going to be aluminium, it will be steel. The likelihood of the leapfrog effect is already reduced. So you may be able to get away with that less harshly tested product. But what we'll usually be looking at is this Type A, where we're looking to protect that spandrel panel using that 1364 Part 4 test data and using products to form that panel to prevent the leapfrog effect, which is where we actually have a system of multiple components which upgrade that spandrel panel to a fire-resistive panel. It's what we use in those tests, which is our fireboard, essentially. But enough about curtain walls. I think I've gone about those quite long enough. Now for ventilated facade systems, so cladding or rain screen. Obviously, it goes in the name that these systems that have a cavity and they have ventilation and drainage. You get water ingressing into the system. You have air rotating around and cycling around in there. And it's important that we don't stop that air cycle movement and we don't stop that drainage, because as soon as we do, that's where things start to go wrong. You get mould starting to grow, panels start disintegrating, and it starts weathering the building very rapidly and damaging the different materials. So we can't just put a conventional fire stop or cavity barrier in there. A bit over the top there with a puddle of water, but it gives the idea. So this is where we have these open state cavity barriers. And the idea is they'll sit there and they should be manufactured, and we manufacture them to be unreactive to anything but heat. And they sit there and they'll just do nothing unless a certain critical temperature is reached within that cavity. And for our product, that's 130 degrees Celsius, which is, again, quite low in the event of a fire. In fact, we commonly get asked when we supply markets such as in the Middle East, is it going to set off just from the heat of the day, which is a little bit too high for that. But at that critical temperature, that intumescent material on the front face, which actually has a very low rating or Euro classification because it's very reactive to fire, which is where I was going before, that reaction of fire and fire resistance are two very different things. That's very reactive, and it starts expanding at that temperature that it reaches. It doesn't actually need the flame itself to reach it. It's just the temperature around it starts reacting. And then that grows and grows and continues to grow until it closes off that ventilation gap. And that then is blocking that fire and that smoke from actually travelling through that concealed space, through that cavity anymore. Obviously, once they've been activated, that's it. They are only a one-time use, but usually you're replacing a lot more than just the cavity barriers if it's gotten that far. But the idea is that this will really reduce, and we see from these system tests that we looked at earlier, these large sort of 10-metre tall tests, you have multiple cavity barriers up that test, and the fire just never travels that far up there with other components that are working together. So if you've got a weak point, there'll always be a weak point. The cavity barriers will always ensure that it's another element that will be the weak point. As long as the cavity barrier is tested right, it's tested in systems, it's tested to its own properties, and crucially it's installed correctly, which is a big important part as well, is it will then make sure that as a system working together, that fire and smoke will be slowed down as much as it could possibly be slowed by. Another important part with these ventilated facades is, as I say, with this air movement, something that again we notice quite a lot is there's a lack of vertical fire stopping or cavity barriers within there. You might find horizontals at the floor slabs, but not having these horizontals. In the UK, the way that we look at these cavity barriers in cladding or rain screen is they are at every compartment line, whether it's vertical or horizontal. And we also actually even say that if there's a larger than or a significant distance between vertical barriers, you've actually got to put another barrier in, even if it's not a compartment line, what we call subdivision. And the reason for that is, first of all, fire can travel sideways. And as we've seen in many of the terrible fires that we have recently in media, the fire can travel very significantly across a building and start avoiding elements that are stopping it from going up. So this vertical compartmentation is also absolutely crucial. But they also form another very important function, which is the drainage aspect and that air circulation. Because we find a lot of the time without these vertical barriers in there, it allows for this air movement to become, rather than just the stack effect, which is what's supposed to happen behind the panels, but it allows the air to actually start moving sideways and pushing some of this water vapour and this condensation around windows and into spaces where it gets trapped and then starts developing mould and degrading the building. So the verticals actually have a much bigger function than just stopping fire and smoke. Again, there's a lot of movement. They're lightweight panels, so it is the same principles that we use on our vertical barriers as we do with the curtain wall fire stops. Is it allows for that movement, it allows for that deflection without degrading the building or degrading the barrier's performance over time. And they are in a zone which gets moisture as well. It gets wet. It needs to be able to put up with that, and again, the products still function after being exposed to water. There isn't any regulation saying that has to be done, even in the UK. We as a company think that it should be, and again, making that point where we should be testing sometimes beyond what's called for as a minimum for regulations. We should be doing what's right, age testing these products, and then testing them side by side with brand new products in the furnace to make sure that even though they've been, and unfortunately artificial aging is sometimes the best you can do, it's still been aged, it's still degraded, but it's still going to give you that performance all those years later that it's installed in the building. Because again, it's crucial, you never know when the fire may happen. Hopefully never, but it can happen. And there's just essentially a couple of details there showing what you may come across quite often, especially with tiled systems. You have very small gaps. Again, we test products to smaller gaps that still allow for ventilation. The vertical product's very easy to use and cut, so it can actually be used again in very small and even these shaped tile arrangements. So there's a lot of products there that can sort of help with giving this compartmentation and protecting our facades. You'll be glad to hear that is the end of the presentation. Hopefully you've kept with me for a little while. I am known to talk for a long time, so hopefully that's been useful to you.
Thank you, Barnaby. Yeah. What would you advise building owners to regarding the fire safety of their facades? What should the building owners do?
Building owners, especially of existing buildings, should be checking the OEM manuals, seeing what's actually on the building. One of the things we've found from a lot of buildings or projects that are historic projects as well is that the products that are in the manuals and the handover documents aren't actually what's on the building, and that's worldwide. So finding labels to things, we put our logo all over our products, so like many manufacturers do, finding logos, finding out what products are actually there, calling the manufacturers, get them in to visit. Any manufacturer with any credibility should be happy to come to the site or send a representative to come and check what's there, and then it can be worked out and assessed whether there is a danger or not.
One of the things you mentioned that it has to be applied correctly.
Yes.
Are there any specific risks that you are referring to, especially if people are going to start in the Netherlands with that are not exactly familiar with how it's installed usually? Because I think that's going to be the practice a lot.
That's a fantastic point. It's something, again, as a company, we are very invested in. We actually have, in the United Kingdom and a lot of our worldwide representatives are trained in how to train installers, how to actually fit the material and inspect it. And we actually even have an app that you can get on your phone to inspect our products, to check, and it sends a report to us, our technical team, that will then assess the photos and the questions that have been answered and see whether it's been installed right. But as you say, it could be the best product in the world. I'm not saying ours is, but it is. But it could be the best product in the world. If it's not installed right, then it's not going to work. So it's very important, and I'm really happy you raised that point. So again, any manufacturer worth their salt should be happy to help installers, especially new customers, in how to use the product. Guides, installation instructions, things like that as well, should all be available from that company.
Okay, you're very clear. Thank you, Barnaby.
Thank you very much. Thank you.